Now we are going to prove another theorem about matchings in bipartite graphs related to a concept of vertex cover. This is one of the first examples in this course of what's referred to as a min-max theorem, which is that we're going to prove that the maximum of some parameter is equal to the minimum of another parameter. In real-world applications, the reason why you would like such a result is because then if you're trying to prove that the parameter has a specific value, you can just find a large example, in this case a large matching, and then find a minimum vertex cover of the same size, and then the theorem tells you they're the same. But first, a vertex cover is a set Q such that every edge is incident to some V in Q. So the idea is that you've got a set Q, and the point is every edge has at least one endpoint in Q. So you can't have anything out here. So given a matching, first we need to prove the following proposition. Given a matching M and a vertex cover of Q, the size of M is at most the size of Q. And here's the proof. For each E in your matching, there has to exist a vertex in Q that's on E. In other words, Q is a vertex cover. So for each matching, you must be able to find an endpoint in Q, possibly both endpoints, but at least one. So for each edge, we're going to choose its endpoint in Q, one of its endpoints in Q, and call it V sub E. And so then the second part is given another edge in M. If V sub F is equal to V sub E, then you have two incident edges, which is not possible. So in particular, by replacing these edges in the matching with these endpoints in Q, we get another set of the same size as M. But since this set of vertices is a subset of Q, we have to have this set is at most the size of Q. And thus, in general, we have this inequality. So my min-max theorem has to do with what happens with bipartite graphs. So suppose we have a bipartite graph, then the size of a maximum matching is equal to the size of a minimum vertex cover. So in other words, we can actually get equality with for bipartite graphs. And the only time we get equality is if the matching is maximized and the vertex cover is minimized. So the point is if you wanted to show that the size of a maximum matching was 6 in your graph, all you would need to do is give me a matching of size 6 and a vertex cover of size 6, and then quote this theorem. All right, so let's do the proof. This one takes a little bit of effort. Note, since G is bipartite, I'm going to have a bipartition into parts A and B that we referred to in this proof. And so suppose we have our maximum matching. We are going to use the concepts about alternating and augmenting paths because it's a maximum matching. And one thing we already know from the previous proposition is that every matching is smaller than every vertex cover. And so to finish this proof off, once you have a maximum matching, all we need to prove is that you can find a vertex cover of its same size. So since that thing has the same size as M, this vertex cover has to be smaller than every other vertex cover, making it a minimum one. And so all we need to do is find a vertex cover with as many vertices as there are edges in the matching. And that is going to be our goal. So we're going to split the graph up into pieces. So we have our bipartition A, B. Inside of A, we're going to create a set called U, and U are going to be the unmatched vertices of A. So the matching might miss some vertices in A, and that's U. That means everything else outside of U has to be matched to something in B. And unintuitively, for B, we're not going to take the matched endpoint as the set we're interested in. Instead, we're going to look at paths that start in U and are alternating an end in B. And for each of these endpoints, we're going to call that R. So our set R is going to be the set of vertices that are on the end of an alternating path that starts in U. Note here that this R can also include vertices down here. All right, so we have our subset. The other last thing we need to note is that by construction, U is a subset of R because of trivial paths. So we need to find our vertex cover. And the claim is that our vertex cover is given by taking the things in A that are outside R and the things in B that are in R. And so we're going to need to claim that this is a vertex cover, and we're going to need to claim that it has the same size as M. So we'll prove that second fact first. Let's take a vertex that's in A take away R. And in particular, it's not in U, and so it's saturated. So every vertex in the red splotch is incident to an edge in the matching. Similarly, let's take a vertex in B intersect R. By construction definition of R, there has to be an alternating path starting in U and ending in the blue stuff. More importantly, if it were some sort of path that alternated as so, and this vertex was left unsaturated, then you would now have an augmenting path. And since we're assuming M is maximum, that is false. So not only do we have this alternating path, but we know that this endpoint in B intersect R has to be incident to a red edge. So this shows that every vertex in Q is incident to at least one edge in the matching. And clearly vertices, distinct vertices in A here have to belong to distinctly different matched edges. And two pairs of vertices in R intersect B have to be matched to distinct edges. The one concern you might have is that there could be an edge in the matching from the red to the blue. But if that were so, then you could take your alternating path to the vertex in B in the blue stuff, B intersect R, and you're guaranteed that there's this matched edge here to this vertex down here, and congratulations, you have an alternating path starting in U and ending in this vertex, which means this vertex should have been in R. But we chose to define it so that it wasn't. And thus we're guaranteed every vertex in this set belongs to a distinct edge in the matching. So the size of this set is at most the size of the matching. And so then we need to show that Q is in fact a vertex cover. And then based on the previous proposition, we're guaranteed that Q is exactly the size of M. All right, so let's show that Q is a vertex cover. So what do we need to do? We need to take an edge in our graph. So it has to have an endpoint in A and an endpoint in B. Let's call those points vertices U and V. If U is not in R, U is in A take away R, so U is already in Q, and in that case, this edge is covered. So suppose that U is in R. So what do we need to show? We need to show that V lands in the blue stuff. So V has to be in R. So then we are in this scenario here where now I can label these vertices as U and V. The point is, since U is in R, there has to be an alternating path from some X in capital U to this vertex U. Note here that X is unsaturated and U clearly is saturated. And then we add this edge to the path. And if V were unsaturated, then we have an augmenting path, which contradicts the assumption that M is a maximum matching. So in particular, there has to be a red edge coming out of V. But more importantly, since V is an endpoint on an alternating path, V is also in R. And it's in R intersect B, so it is in Q. Thus, Q is a vertex cover and has to have the same size as the maximum matching. Finally, we're going to end with some applications. So this is actually Hall's original theorem. what you have is you have a set X, and then for some indexing set I, you have a collection of subsets of X. So for each integer or element I, you have X sub I as a subset of X. Then, given this setup, a system of distinct representatives is a choice of elements with the property that Vi is an Xi for all I, and Vi is not equal to Vj. So the idea is you can think of this as a bunch of committees, and a system of distinct representatives is choosing a subset of people so that you have exactly one person from each committee. So what was Hall's original marriage theorem? It's determining when such a collection has a system of distinct representatives. His original claim was that this would happen if, for any subset of committees or the indexing set, the size of the union of those committees is at least the size of the indexing set. In particular, any individual committee has to have at least one person on it. Any pair of committees has to have at least two people in the union, and so on and so forth. So the modern proof of Hall's theorem is to construct a bipartite graph with one part of the bipartition being X, so the people, and the other part being the indexing set, so the set of committees. And then you're going to create an edge between person V and committee I whenever person V was on committee I. And so then what we actually prove is that suppose we have a system of distinct representatives, then you can see that V sub I forms a matching, which saturates I. This is true by the condition that we say Vi is not equal to Vj whenever I is not equal to j. That guarantees these edges are independent. And we also require that there was a Vi for each I, and so that tells you it saturates I. Conversely, suppose you have a matching M which saturates I. Then if you look at the endpoints in the matching that are in the set X, you're going to get a distinct system of representatives. And so the point is that matchings correspond to distinct disjoint systems of representatives, and thus such a system exists if and only if this bipartite graph has a matching which saturates I. So then we can use our Hall's marriage condition. So this happens if and only if the neighborhood of S is at least the size of S for every subset of I. But what is the neighborhood of S? Well, it's all those vertices with the property that V is on committee Xi for some I in your indexing set. That should be an S here. Which means it's the union of the committees. And so translating Hall's marriage condition back into the original definition in terms of disjoint representatives, N of S is equal to this set, and then you see you have the condition we had before.